In this example, we're asked to look at the free vibration of a beam which is clamped on the left side, has a roller connection there on the right side. So it's basically a cantilevered beam with an additional support there on the right-hand side. We're supposed to find the natural frequencies in mode shapes. What we're going to do is begin the process, as we always do, by recalling the equation of motion for the beam for constant cross-section, constant properties along the length. The equation of motion is a partial differential equation of EI times the fourth derivative of the displacement W with respect to x plus rho A times the acceleration term, and the right-hand side is a 0. This solution, we're going to write the solution in a separable form where we have a function of x, w, times a function of time t of t. And if we put that into the solution, we have EI, the fourth derivative of w with respect to x, t, plus rho A, w, times 2 time derivative of t is a 0. So since this is a separable solution, we're going to separate out the spatial part over on the left-hand side, EI over rho A, w fourth derivative, function of x, divided by w itself. The right-hand side will be t double dot divided by t. Since the left-hand side is strictly a function of x, the right-hand side is strictly a function of time. In order to have those two equal to each other for all space and t, it must be a constant. We'll write the constant as the minus number there of minus omega squared. So the two equations we get back are t double dot plus omega squared t is a 0. As we've done before, we know the solution of this is cosines and sines. The spatial part of the problem, that equation is the fourth derivative of w plus rho A over EI times omega squared, and we'll call that beta to the fourth, as we've done before, times w is a 0. And as we've seen before, for other problems with constant properties, the solution for this spatial part of the solution is a cosh beta x plus b sinh beta x plus c cosine beta x plus d sine beta x. So what we need to do for this is to enforce our boundary conditions. So if we enforce our boundary conditions, the displacement condition on the left-hand side of no displacement says that in its separable form, capital W must be equal to a 0. So we set x equal to a 0 on the right-hand side, and we simply get a plus c must be equal to a 0. So we know that there is a relationship of a equals minus c between those two coefficients. We have the no slope condition. So partial w with respect to x on the left-hand side, written in terms of its separable form, is w prime at x equal to a 0. Being equal to a 0 implies that w prime at x equal to 0 is a 0. So that gives us beta times b plus d. And so we will assume, as we have in the past, that beta is not equal to a 0. In the end, we go back and check to see whether that's true. But for beta not equal to a 0, that means that d is equal to a minus b. Those are the same two equations we had for the cantilevered beam. the right-hand side, the displacement at x equal to L, written in its separable form. We know that that product of those two is a 0 for all time. We know then that therefore W itself must be equal to a 0. So that's A cosh beta L plus B sinh beta L plus C cosine beta L plus D sine beta L. So that is our third equation. And finally, there's a pin joint there, a roller connection. It says there's no bending moment that's applied there on the right-hand side. So EI second partial W with respect to x at x equal to L, written in its separable form, W double prime at x equal to L, that is a 0. So therefore, for all time, then it says that the second derivative of W with respect to x on the right-hand side must be a 0. So what we get is a beta squared coming from all the terms. The cosh becomes a cosh. The sinh becomes a sinh. The cosine becomes a minus cosine. And the sine becomes a minus sine. So this is our second equation coming from the right-hand side. Okay, so what we have is, again, we've made the assumption for right now that beta is not equal to a 0. We have that equations 1 through 4 give us the following two equations, which I'm going to write in a matrix form: cosh beta L minus cosine beta L in the 1, 1 position, sinh beta L minus sine beta L in the 1, 2. In the 2, 1, it's cosh beta L plus cosine beta L. And the 2, 2 is sinh beta L plus sine beta L. And this gets multiplied by our coefficients there of A and B. It's a homogeneous set of equations. So in order for that to be a 0 and for a non-trivial solution for A and B, because we know if A and B are a 0, so are C and D, which means that we would have a trivial response. If we throw out that, what's left is that the determinant of that 2 by 2 must be a 0. So therefore, if I expand this out, I get cosh beta L minus cosine beta L. That gets multiplied by the 2, 2 term, which is sinh beta L plus sine beta L. If I multiply then the 1, 2 times the 2, 2, this is sinh beta L minus sine beta L times cosh plus cosine. So that is the determinant of that 2 by 2. Let me expand out that. What I'm going to do is write this as cosh beta L minus cosine beta L. That's from the first part, minus cosh beta L minus cosine beta L. That all gets multiplied by sinh. And then that which multiplies the sine beta L, that is a cosh beta L minus cosine beta L plus cosh beta L plus cosine beta L. So that is just an expansion of that 2 by 2, but written in this form, we can see that this cosh and that cosh will cancel each other out. This cosine cancels with that. And so in the end, what we're left with is cosine beta L sinh beta L is equal to cosh beta L times sine beta L. So that's our characteristic equation. Can write that. If I divide both sides through by cosh beta L and cosine beta L, my characteristic equation becomes tan hyperbolic tangent beta L is equal to tan beta L. So this is our characteristic equation. We need to solve that. There are not closed form solutions for this, so we'll have to rely on MATLAB to give us the answer. So what we will do, as we have in the past, is make a sketch. So to help us with this sketch, recall that hyperbolic tan, which is defined as a sinh divided by cosine, that becomes E beta L minus E minus beta L divided by E beta L plus E minus beta L. So the conclusions that we draw from this is that the hyperbolic tan at beta L equal to 0 is a 0. That's easy to see because the top two terms cancel each other out. The limit on the other side, when beta L becomes large, of tan beta L is a 1. Because when beta L becomes large, it becomes the exponential divided by the exponential. So that's a 1. And we can also say that the derivative with respect to beta L of tan beta L is the same as the derivative of hyperbolic tan with respect to that. So when we make the sketch here of tan, we know how that looks, I think. The hyperbolic tan, we're going to use those results there to make that sketch, and the last one to show the relationship between the two functions over there on the left-hand side. I should say that this is true when beta L is a 0. Okay, so let's make the sketch that we generally make. So I'm going to plot on the horizontal axis beta L. Tan, we know how that looks. Let me make some construction lines on here. Let's draw some lines here for values of pi over 2. So these are lines which correspond to integer multiples of pi over 2. The tan function starts out at a 0 and goes to infinity there at pi over 2. Comes in from minus pi over 2, crosses over at pi, and goes up like this. It's a function that repeats itself like this. So this is our tan beta L. Now our hyperbolic tan, we know it starts at a 0. It ends up on the right-hand side at 1. So what I'm going to do is draw an asymptote here at the top there at 1. So this corresponding to 1. And so that is going to be looking like this. The hyperbolic tangent looks like this. And this result right here means that these curves look like that. They start at the same point with the same slope. So there's no crossing there. The first crossing doesn't occur until here. This is our first root of beta 1L. This is our second root of beta 2L. This is our third root of beta 3L, and so on. So the blue here, again, is hyperbolic tangent of beta L. So there are no closed form solutions for this, so we will use, as we have in the past, use MATLAB to solve. In order to use the functions there in MATLAB, we need to provide it with some initial guesses for the appropriate roots. So the initial guesses we would make is that put in values of beta JL, which are the inverse tan of 1, the different roots of that. Because we can see here that they're going to be close to when tan is equal to 1. So all these roots, in fact, as you go to higher and higher roots, they asymptotically approach those roots there, inverse tan of 1. So that ends up being pi over 4 plus integer multiples of pi. So use those as the initial guesses, our modal functions. Keep in mind that we have the roots of our characteristic equation. We've got the values there, or we will get our natural frequencies from the roots of the characteristic equation. But when we get through, we still need to have the modal functions. So don't forget that the modal functions are what we have here, the A cosh, the B sinh, the C cosine, and the D sine. We have seen that the CJs, those are equal to the minus AJs. And we saw that the DJs in a similar way were equal to the minus BJs. And equation 3 above tells us that WJL which was equal to AJ cosh beta JL plus BJ sinh beta JL plus CJ cosine beta JL plus SJ, not S, I keep wanting to say S there, that is the D J sine beta JL. So again, this was equal to minus AJ, and this is our minus BJ. So from this, we can solve for BJ in terms of AJ. So BJ is cosh beta JL minus cosine beta JL divided by minus sinh beta JL plus sine beta JL, all times AJ. So we know what CJ is in terms of AJ, BJ in terms of AJ. So what we can do, therefore, is write down the result of this. And so the jth modal function is going to be a coefficient AJ in front, cosh beta JX minus cosine beta JX plus that big expression up there, cosh beta L minus cosine beta JL divided by minus sinh plus sine times sinh minus sine. So these are our modal functions there, Wj. This coefficient Aj at this point, it's arbitrary as long as we don't set it equal to a 0. So I'm going to set all those coefficients exactly equal to 1. In the end, our response is going to be that the response W as a function of both x and t will be the linear combination of all of our modal functions times Cj cosine omega jt plus Sj sine omega jt as that. So what we need to do is enforce our initial conditions then to find the coefficients of Cj and Sj, and we will use the orthogonality of our modes. We really don't have explicitly what our modes are, but what we do know from our lecture is that the for the self-adjoint boundary conditions that we have got, the modes will end up being orthogonal. So this problem here is very much like all the rest of them that we have done. What we do is we write the solution in a separable form. We enforce our boundary conditions on the spatial part. We get our relationships that exist between our coefficients of A, B, C, and D. We get our characteristic equation, and from that we have natural frequencies and modes, and therefore we have all the pieces that it takes to put together a free vibration response of that beam.